If you need one, just raise your hands, and they will see if they can give you some USB cable. So everybody is okay with the boards, right? What you can do is, or maybe we can do a sanity check now. Go ahead. You don't need to plug the shields yet. I mean, one thing that we can try to do now is just plug in the what you call this, the NuCleo board, and double check the device manager and make sure that the 3 points, the 3 enumeration is there. Okay. Just plug in and check the device manager. Make sure the USB drivers are properly installed. Let's take about maybe 2 minutes to do that, to verify. There are spare NuCleo boards here, but no shield. Okay? Just the NuCleo board. If you want to play around with just the NuCleo board, now, cable no more. So if you want to play with the NuCleo board, just the NuCleo board. Just so you know, okay? After the workshop, okay, listen up. After the workshop, we're going to collect all these boards, okay? So just, you understand. We are going to collect all the boards back, including the shields, and then we will call a representative for each company, and we will give one set for each company, okay? Sorry, we cannot afford to have every one of you to have one shield, one board. So we're going to give one shield, the shield and the board for each company, okay, at least one set. Right? So we're going to take it back at the end of the session, and then we redistribute again. All right? Okay. All right. So what do you expect? What will you expect? Sorry. What will you expect when you connect the board? You will see this LED in red. See the one near the cable. At the first connection, you will see a blinking LED, this red one. Okay, it means that it's trying to enumerate the USB, and the system should be able to install the library. Once it's a solid red, usually it means that the USB drivers are installed. Okay? But you still need to what? You still need to verify in the device manager to make sure that the embed is there, the virtual COM port is there, and the ST-Link dongle is there. Okay? Who has problems? Who has problems with the USB drivers? Come on, raise your hands if you have one. No problems. Very good. USB driver. Okay, this is a show of hands. The quickest one wins. Who doesn't have a USB cable? No, okay. I have only one spare, so first one to raise your hands, will get it. Okay, so if you don't have any problems with the USB installation, if everything is okay, then we can proceed. Yeah, I will go through this a bit quick on the core and system overview. All right. This is to show the Cortex M0 Plus. Okay, just a summary, a very brief summary only on what the Cortex M0 is all about. Okay, so this is a core architecture from ARM. We license it from them. So in total, we have Cortex M0, we have Cortex M0 Plus, we have an M3, an M4, and an M7. Okay? So the latest one is the Cortex M7 based STM32. We call it STM32 7. So that's the latest one that we have, and that's the latest. The M7 is the latest core that we have licensed from ARM. So we are using the core from ARM to power the device as a CPU, and the rest of the peripherals we design ourselves. Okay. So let's have a look at the Cortex M0 Plus architecture. The main points here is that for you to understand, especially when you are comparing from M0 and M0 devices and M3 devices. One is that the Cortex M0 is a von Neumann architecture. It has only one bus going up. versus that of the ARM architecture of the M3 and M4. Okay. One of the great things about the Cortex M series is that it integrates the interrupt controller, which means it's part of the core itself. We are not designing the interrupt controller outside the CPU. Okay. The interrupt controller is part of the MCU. Okay. You have the core itself has deep sleep modes that that we use as a baseline to create our own system, low power implementation. Okay, and then you have also debug capability. So this specs here is basically coming from ARM, and we just use the specs. Okay, so you have NVIG, you have thumb and thumb 2 support, which means it is binary compatible with M3 and M4. You have SWD as a debug interface for the M0 and also for M0 Plus. Okay. This is a architecture. This is the block diagram basically showing the nested vector interrupt controller. So this box here is the entire Cortex M. So this is a generic block diagram. So you have the CPU or the core here, and it has a direct connection, or it's closely coupled with the NVIC. And from there, you will see interrupt lines going from the peripherals itself and then going to the NVIC. So here, the advantage of having the NVIC as part of the core is the reduced latency in handling interrupts. Okay? If you compare it with ARM 7 or even ARM 9 before, this Cortex M has what? Improved the latency, okay? Shortened the latency of about 65%. So instead of having a couple of 20 something cycles to jump to the interrupt routine, it will only consume about 16 cycles instead of 20 plus, 20 over cycles. Okay? So the latency here is no longer there compared to that of the interrupt controller implemented outside. Okay? So I will, okay, before going to a certain point, I would like to point out in the end. The debug capability of the Cortex M, for at least for the STM32 F0 and L0, we are using only the SWD. Okay? 2 pin debugging. So at least you have your pin is optimized, and take note, the SWD can be configured as normal GPIO. Okay? By default, when you reset or when you power on the device, these pins are debug pins. Okay? So no matter what you do later on, whether you want to reconfigure it as a GPIO or something else, at least you have the debug capability when you power on or when you reset the device. Okay? So here, you only have 2 pins, while on the other devices, for example, the F1 series, F2, F3, F4, you have 2 modes of the debug pins. Okay? You have JTAG, which is usually 5 pins. Well, you can optimize it to 4 or 3. Then you have SWD as well. Okay? But those are for the Cortex M3 and M4 based STM32. Okay? Our F0 and L0 only supports SWD, 2 pins. Okay? Alright. Let's have a look at the system architecture. So now, we are looking outside the Cortex M. So, if you remember, I mentioned earlier, the Cortex M0 and M0 Plus has only 1 bus going out of the core. So it connects to the rest of the blocks, okay, of the STM32 through what we call a system bus. Then it connects to a bus matrix, and then it connects to the rest of the blocks, okay, or the buses of the STM32. AHB or Advanced High-Speed Bus, and you have peripheral buses as well. So you have 2 peripheral buses, ATB1 and ATB2, and each you can configure with different frequencies. Okay? So here you have DMA, and you have the peripherals connected to the different peripheral bus, and you have the flash here, okay, connected to a flash interface, and then connected to the bus matrix, okay, including the SRAM. One thing that is unique on the M0 and M0 Plus is a direct connection. A bus, a CPU has a direct connection to your GPIO registers. We don't have this on the M3 and M4. Okay, it doesn't have this feature. All right. Now, documentation for the L0, where you can find them. You just need to key in st.com/STM32L0. And from there, on the left side, under the resources, you'll see documentations there. And you'll see application notes, programming manuals, and reference manual and data sheet. Okay? I highlighted 3 different documents that you can download. They're usually the ones that you use. Okay? You will use. 1, your reference manual. Okay? Reference manual contains or includes the functional description of each of the peripherals. Meaning here, you will find the complete documentation of each of these peripherals, including register description, okay, and pin description. Okay, and then from there you can use it as a reference to configure your peripherals in the CubeMX. Okay, because here in the reference manual you have a complete description of the different nodes. Okay, the data sheet. Okay, what's the difference between reference manual and data sheet? The data sheet only contains or includes device overview, functional overview, pin description, memory footprint or memory mapping, and electrical characteristic only. Okay, it does not describe, it only gives you a very brief description of the peripherals, and that's it. Okay, so if you want to learn or if you want to understand how the peripheral works, what are the different registers and the description of each of these registers, you'll have to look into the reference manual. Okay? Now, the programming manual is different one. This one here is for the Cortex M0. So if you're looking at documentation for the Cortex M0 core, you can download a documentation from ST, okay, which is a compressed version of the Cortex M0 technical reference manual from ARM. Because the Cortex M0 is from ARM, right? So you can download the full documentation from their website, okay, from ARM website. But we do have a ST version of that technical manual, okay? So it's less number of pages to summarize versus that of the technical manual from ARM. So you can use, usually I would make use of this and this. Okay? Here in the Cortex M0 programming manual, you will find a description of the NBIC. If you want to understand more about the NBIC, go to this document. Okay? Where can you find these documents again? From st.com/STM32 L0. Okay, good. I'm trying to make sure that you're still awake. All right. So here, just key in, and you can see several other documentation and also software packages as well. So you go to the different categories and you should be able to download some more stuff there. Okay? Alright, so let's have a look at the reset and clock control quickly. This is one of the things that you usually configure, but RCC or reset and clock control is a section, okay, in the reference manual. So this is just an overview of the reset sources of the MCU. So you have the reset pin here, and it goes to the system reset. But take note also that there are internal reset that can trigger a system reset. You have a pull-up here, internal pull-up, so it means you don't need an external pull-up on the reset pin. You only need a capacitor there. That's it. Okay? So there is also a register, a status register, that will tell you which one of this, which among these reset sources is triggering or triggered the interrupt, okay, or the triggered the reset. So at least you have you are able to know what triggered the reset, whether it was triggered by the watchdog, whether it was triggered by a noise coming from the pin, okay, an intentional reset. So at least you can debug something, okay. Now the most important part is the clock scheme or the system clock. This part here for the L0. You have a maximum of 32 megahertz of system clock, and you can have several clock sources. You can select several sources. Okay, the default source is the MSI default at 2 megahertz. So when you reset or when you power on the device, the clock for the system, the first, when it executes the code, the system is running at 2 megahertz until you reconfigure it to something else. Okay, remember in the CubeMX, you configured to 32 megahertz. So before it is being reconfigured to 32 megahertz, the system clock is running at 2 megahertz. Okay? From here, you can actually select several sources. You can have 16 megahertz from the high-speed internal clock. It's an internal RC, which means you can just, you have the option to not to use an external crystal. Okay? You have also the option to make use of the external crystal directly, or make use of the PLL, okay, to increase to the maximum frequency. And the PLL has two sources. Either you get it from the internal RC, or you get it from the external crystal. Okay? So in the CubeMX, you have, you select this. Which sources do you want? Okay? From there, you have 32 megahertz. It goes to a prescaler for the high-speed bus, okay, for the bus matrix. And then it goes to the different peripheral buses. So you have prescalers here, another prescaler for the P clock, peripheral clock 1, and peripheral clock 2. Okay? For this, you have 32 megahertz as maximum frequency as well. Okay? Alright? The other clock source, or the other clock source that you will see is the low-speed internal clock, about 37, 38 kilohertz. This is mainly used for the independent watchdog. You can also make use of this for the RTC. But again, if you use the internal RC for RTC, the accuracy is not there. If you are just using it for just a wake-up counter or auto wake-up unit, okay, for the auto wake-up unit, then you can make use of the LSI, low-speed internal. But if you're using RTC for calendar, for dates, for timing, then use the external crystal. Okay? So all you need to do, if you want to use these external crystals, you have to enable the pins in the CubeMX configuration. Then you will find this in the CubeMX configuration. You just need to select, go to RCC and say, I want a crystal in there. I want to use an external crystal for the high-speed external, and then low-speed external as well. Okay. Then you have RTC also coming from the high-speed external if you want. Okay. If you don't want this, you can get it from the high-speed external crystal. Now, the clock security system, okay, is a feature that you can enable in the STM32. And the main purpose or the main objective of the clock security system is to monitor the, let's say, monitor the external crystal, such that if the crystal frequency is lost, meaning some disturbance, a very big disturbance, or the crystal got damaged, the clock security system will detect this event, and it will switch the clock source for the system clock from the external crystal, and it will switch to the internal crystal or internal RC automatically by hardware. So this is a feature that allows you in the end, that allows you to auto recover from a damaged external crystal. Or if there is a disturbance, let's say there's a very strong ESD, okay, that is induced into your system that caused a what you call this, a problem on your external crystal. You know, it sense it stopped oscillating, or the frequency is no longer valid, etc. Then the clock security system will detect that event and automatically switch to internal RC and triggers an external interrupt, triggers a non-maskable interrupt. So at least in the non-maskable interrupt, you can say, okay, shut down mode because my external crystal is no longer valid. I don't want to execute my system in an invalid clock source. Okay, so at least you have a safe shutdown. Or you can also wait until the external crystal is stable. Then you can switch back to your external crystal when it is stable. So here you have the possibility to what? Auto recover. Okay? Same is for the external low speed external clock. Okay? You have also a clock security system there. The other features that you will also see on the clock scheme is that you have the possibility to output some of these clock sources, some of these frequencies, and output it to a particular pin called MCO, or multi-clock output pin. Okay, one of the purposes of using MCO is for number one is for debugging purposes. Okay, to measure what is really the actual frequency inside your system. Okay, for debugging purposes, let's say you are generating a PWM and you're not generating the correct frequencies. Okay, so you can verify your system clock by enabling one of the MCO pin. Okay. The other purpose for the MCO is to connect it to what? To an external circuitry. You use the STM32 as a clock source for an external chip. Okay. Instead of implementing a separate crystal, you can remove the crystal for that chip and make use of the STM32 as the clock source. Okay, so that would optimize your BOM cost. Okay, then you have different clock sources for these different peripherals. Okay, questions on the system clock? Right. Lunch, which we already had. So skip the lunch. GPIO. One of the peripherals that you will use. Okay? Definitely. So this is a summary of all the features. Just some points there. One is most of the pins are 5 volt tolerant. Okay, most, not all. Okay. All pins are configured. All pins are GPIO, okay, except for those SWB pins, which are debug pins upon reset. But all of them are input floating as default. Okay. So when you power on the device, when you reset the device, the pins are input floating. So hardware people, you need to take note, because it's not going to drive your external circuitry when you turn on or when you reset the device. Okay? It's input, which means what? High impedance. It's not driving your output. So if you are driving a particular DC motor, a very small DC motor, better have a pull up or pull down to keep it from running while you are still resetting and reinitializing the system. Okay? So just take note. Each pin can be configured as GPIO input or output, or you can configure it as an alternate function. What do you mean by alternate function? It means that you reconfigure the pin as USB or SPI or ADC function. And these are what we call alternate function. Okay? So you configure the pin as alternate function first before you configure the peripheral. This is the diagram, okay? Each pin will have something like this. Alright, and there are several modes. So depending on the mode that you set for each of these GPIOs, you can have output mode and you can have pull up or pull down. And these diodes here are protection diodes. And when you configure it as an output, this output driver becomes active, and the input, as you can see, is still active. So which means whatever logic that you put in here, you can read it back through the input data register. You can set it as output push-pull or as an open drain. If you configure it as an alternate function, both of this section, depending on the alternate function, you will see a connection here. Okay? So which means if you configure it as a USART RX, for example, meaning input, the signal will actually go through here, and it will go to the USART or UART RX RX register. Okay. If it is an output like TX, then it will make use of this pathway. Okay. If you configure it as an input floating, the output driver is off, and you will have here. You will have this input driver active. As you can see, you have a switch trigger here. Okay. So which means if the pin is input floating, like when you reset, okay, and if the pin is left hanging, it's not connected anywhere, this pin will capture some noise and it will trigger the switch trigger. And while this is toggling, high low, it will consume current. So especially for low power implementation, you can connect this pin to ground to make sure that it will not trigger the switch trigger, and also it's much safer. Okay? Or you configure the pin as analog mode. This is to disable the switch trigger if the pin is configured as analog mode. So that would be this configuration. If the pin is to be configured as an analog channel, like ADC channel, DEC channel, op-amps, comparator, and comparator, the pin has to be configured as analog mode first. Then you can make use of ADC and DEC and comparators. Okay, the connection would be like this: the output driver is disabled, Smith trigger is disabled. So depending whether it's an input, analog input, or analog output, you will have a certain path here. Okay, so these are the different modes of the GPIO. Okay, so these are normal GPIO. Now, you can again configure the GPIO as alternate function. So each pin will have a dedicated alternate function. So if you're using the CubeMX, you can click on the pin and you will see the alternate function there. If you're not using the CubeMX, you can open up the data sheet. You go to the pin description, and there's a table there that shows you what are the different alternate functions for that particular pin. Okay? Now, one of the configuration for the I/O is external interrupt. External interrupt is a different block inside the STM32, and here you can configure its register such that you'll have an interrupt when you are having a rising edge or a falling edge, or both rising and falling. So here you configure the registers to trigger whatever edge that you want, and here you trigger an interrupt when an event occurs. Okay? So this is a mapping of the external interrupts. So you'll see here, each GPIO, all of the GPIO can be configured as the external interrupt, any GPIO. But you have only up to 16 external, meaning you can only enable up to 16 external interrupts. But you can choose any GPIO. Okay? Here? And the rest of the channels for the EXTI are actually internal. So these are connected to programmable voltage detect, RTC alarm, and so on and so forth. Okay? So for external interrupt, the assignment here, so you have EXTI 0, 1, 2, 3 until 15, so 16 all in all. And each of these EXTI channel is multiplexed to connect to the different GPIOs. So if you're using PA0 or PB0, PC0 until H0, it means that you have to use the EXTI 0. So all pin 0 of that port is multiplexed to the EXTI channel. Okay? And you have A1, B1, C1 connected to EXTI1 and so on and so forth. Okay? This is how it is being mapped inside. Now, let's have a look at, let's study a bit when an interrupt occurs, what will happen inside. Or what are the things that you need to configure to have a valid or to have a correct implementation of the interrupt. There are two things that you need to set. One, you need to configure the peripheral side, and you do the configuration for the peripherals. You need to enable the interrupt request on the peripheral side. The peripheral needs to say, hey, I want, I'm requesting for an interrupt. Hey, CPU, I'm interrupting you. Please accommodate me. Okay? Somebody has to raise the flag so that the CPU will handle the flag. Okay? So which means you need to set the interrupt request on the peripheral, and on the CPU side, on the N-bit configuration, you need to open up the channel. You need to enable the channel on the N-bit side. So two things to configure or to enable. Interrupt request on the peripheral, interrupt channel on the N-bit. Okay? Because the N-bit is a different entity. Okay? Let's say. So one thing that you need to configure on the N-bit also is the interrupt software priority. So there are how many priority levels for M0? How many? 4. Okay? Which one is the highest? 0 is the highest. Level 3 is the lowest. On the Cortex M3, how many levels of interrupt? You know? Okay, very good. How many? M3 is. Yes. Yes, it's 250 something interrupt levels. That's by specs. Okay? That's by specs of the ARM Cortex M3 or even M4. You can have that much, an 8-bit interrupt levels. But for ST, we are only implementing up to 16 levels. Okay? So for M0 plus M0 also, there's only 4 levels. So you need to configure that on the N-bit. Now, assuming that you have configured this correctly, what will happen when there's an interrupt? Okay? So here is an example. Let's say on an EXTI or an external interrupt, you're configuring it as a rising edge. When there's a rising edge detected on the pin, the EXTI peripheral will trigger an interrupt request. Okay, so it will raise a flag saying that the NBIC needs to handle. On the NBIC side, it will check. So once it receives this interrupt request, the NBIC will check the software priority of that particular interrupt line. Okay, it will check whether this interrupt has the highest priority or not. If it does not have the highest priority, it will put it as a pending interrupt while it's trying to finish an ongoing higher priority type of interrupt. If it is the highest, then it will It will look into the vector table and it will fetch It will go into the handler and fetch the interrupt routine. Okay? You get me? So once the interrupt is over, it will check again. Who else is raising a flag? Or who else is trying to request for an interrupt. Okay? It will check who is the highest interrupt, or who is the highest has the highest priority. It's not a first in, first out. Huh? So assuming you have 4 interrupts coming in, okay? Then let's say a 5th one comes in, lower priority. So let's say one of the 4 interrupts has been managed, is ongoing, and then the 5th one comes in. Okay? So now, when the interrupt is over for this one, it will check again for the other 4. It's not going to take this one or this one or this one. It will check again who else is having this interrupt. Me. So it will check again for the next highest priority. So if this one, even though it happened on the last part, if this one has the highest priority, then it will be handled first. The other 3 will be still pending. Okay? Alright? Okay, good. Questions on interrupts? Yes? There's no? There is. Which means, okay, so here, okay, let's have a, so now that you're asking, and I don't have a pen, okay. Let's say this 2 peripherals is requesting for interrupt. Okay? There are several cases. IRQ0 and IRQ1, assuming that they happen at the same time. Okay? If they happen at the same time, the NBIT will check which one of these 2 has the highest priority. So assuming that the lower one is, this one is assigned with a priority 0, and this one is assigned with a priority 1. Okay? So if they happen at the same time, we change so if they are firing at the same time, it will check. So obviously, which one of these 2 interrupts will be executed first? It will be this one, okay? Because we have assigned this with a software priority 0, and the other one is 1. Okay? Once the first one is finished, then it will take the other one. So that's the first case. The other case is that, let's say IRQ1 happened first. Okay? Then it will handle IRQ1. Then while it is handling IRQ1, the IRQ0 comes in while it is still handling IRQ1. Now, the NBIT will receive this interrupt request. What the NBIT will do is actually check whether this request is higher compared to the one that is currently being executed. If it is higher, then it will preempt the existing one. So this one here will be stopped. It will be, let's say, it will be interrupted. It will jump to the service routine of the IRQ0. It will finish IRQ0. Once it is done, it will go back to IRQ1 and continue the execution. So there is a preemption here in this case. Why? Because the other one is higher compared to the one that is being executed. Okay? Now, if both of them has they have the same interrupt priority, assuming you have interrupt 1 or IRQ1 executed first, meaning it's already being handled, and then IRQ0 comes in the middle. Okay? The NBIT will receive the request and check again. Do you have a higher interrupt compared to the one I'm speaking now? Since they are the same, the IRQ0 will remain pending until IRQ1 is finished. Okay? There's another case. Assuming that you are having the same IRQ level or IRQ software priority for both IRQs, and they happen exactly at the same time, or both are pending at the same time. So let's say IRQ0 and IRQ1 happen at the same time. Okay? Which one will be executed first? It will be 0. Why? Both of them have similar software priority. They have software priority 0, both of them. Which one will be executed first? Or which one will be handled first? Any ideas? None? Okay. In NBIG, or in the Cortex M, there is a software priority, and there is also a hardware priority. Okay? What do we mean by hardware priority? Hardware priority is a fixed one. Each interrupt line has its own channel, right? One channel for IRQ0, 1, 2, 3, 4, and so on and so forth. Up to 22 lines for Cortex M0. Okay? It means that it has its own channel number. And these are hardware connections. The smaller the channel, the smaller number of the channel, the higher the priority. Which means NBIG channel 0 is higher than NBIG channel 1. So in this case, this one here is connected to channel 0, and this one here is connected to channel 1. If both of them have the same interrupt, software interrupt priority, and they occur at the same time, or they are pending at the same time, then the NBIG will resolve the conflict by moving back to what? Hardware priority. So, check the software priority. Are they the same or not? If they are the same, then check the hardware priority. So, in this case, which one will be handled first? It will be this one. The one with the higher what? Hardware priority. Okay? So, in the end, even though you have the same software priority, it will still be what? Resolved. Okay? In the end. Okay? So, nested interrupt and concurrent interrupts. No? These are the two things. Okay? Questions? None? Good. Hands on. So, the first hands-on for this afternoon, we're a bit really late. So, we're going to do the first hands-on, which is GPIO configuration and the XDI configuration using the CubeMX. We are going to do this from scratch. Okay? To speed up the time, I will help you on the CubeMX first. I will not leave you alone. Usually, I just, okay, lab 1, go ahead. After 30 minutes, I come back and check. Okay, so exception for this session. I will try to do the CubeMX, then the rest you do yourself. Okay? Good? Alright, so let's start. You can find, you can follow the presentation here because each lab is it's complete with step by step, okay, what you need to do. So let me just introduce lab. Actually, this should be 2 for 1. Sorry. What we're trying to implement here is that a push button triggering an interrupt and another GPIO lighting up the LED. Okay? So here we configure one GPIO for the push button and another GPIO for the LED driving. Okay? So this is how internally it is connected. So from GPIO configured as external interrupt, when the edge is detected, it will go to the NBIG to request for an interrupt. Okay? Now, this is the hardware connection inside. So if you look at the schematics of the NuCleo board, you'll see that the push button is active. What level, what edge are we checking here? When you press the button, you will see a what? Falling or rising edge? Falling edge, no? So when you press, it goes down, connect to ground. So you have a falling edge. So you should check for a falling edge when you configure the interrupt. And here, for the LED, when you set it to high, what will happen to the LED? It will turn on. If you set the GPIO to low, it will turn on. Okay, so these two principles. So this is the description. So what you need to do is create a new project from scratch. Then you configure the GPIO. Okay, set the project settings for the CubeMX. Then you start using this. Then you start configuring, okay, configuring the GPIO. So these are the two things that you need to do. One GPIO for GPIO output to drive the LED, and this one here is for the push button. So this has to be what? This has to coincide with your hardware. So take note. You also need to enable the SWT. Then we what? Configure the clock for the system clock at 16 megahertz. Okay. So very simple. Just make use of the HSI as the clock source, and that's it. Okay. Then in the configuration, the profile configuration, you configure the GPIO for driving the LED as output push pull, no pull up. Okay. Fast output speed. You can put some labels if you want, LED 2, whatever. Then the PC13, which is the push button, configure it as an external interrupt mode. Okay? External interrupt mode with the correct edge detection, which is, what is the edge again? Calling edge. Okay. No pull up. Okay? You can put the user label there, V1 for example. Then this one here, you can leave it as default. These are for the default things. The NDIC, you need to enable the interrupt request, or you need to enable the NDIC channel. Remember, peripheral you enabled here using the EXTI, and you also need to enable the channel on the NDIC. So on the NDIC configuration, make sure you enable the external interrupt line. Okay? So there are steps here. You save the project and then you generate the code. Once you generate the code, you can then now what? Write your own user code. So the point here is that you need to add the code to manage the interrupt from the push button and to drive the LED. You don't need to create your own because I created something for you to copy. So here, you just copy all this, the one that are highlighted in red or something, okay, purple, whatever. Copy this, copy and paste to your Cal project. So make sure you put it in the correct user code section. So this one here is to define a variable, and this one here in the user code begin tree, you copy this part, and you copy this part, and then you also need to put the callback for the interrupt, okay, inside the code begin for. Now take note that this, okay, these codes here that you need to copy, there are some missing parameters here. See that question mark? You need to replace it with the correct one. Okay? So that's the essence of Lab 1. You are doing it from scratch. Okay? The main point there is for you to have a feel of how the CubeMX works, and then to generate and write your own user code. Okay? So I'm going to help you. You can follow me by, I will help you with the CubeMX configuration. Okay? Then you do the copy and paste for the user code. Alright? Alright. So, what do you need to do? Let's open up a new CubeMX. So I have an existing one, I will close it. Close the project. I do a new project. And to be quick, you can just make use of the NuCleo board. Okay? Look for the L0 NuCleo board. So here, did you follow? Just let me know if you are if you're lost. Okay. Then select the NuCleo L053RA. Click OK to open up the project. Okay. So now you have already an existing pinout. Okay. What I want you to do is go to Project, go to Settings, so that you can name your project. You can put it anywhere. So maybe we put it lab 1. Okay? Or whatever name that you want. You put your name or whatever. Okay? Your girlfriend's name, your wife number 1 name, wife number 2, whatever. Okay? Girlfriend 1, girlfriend 2. Okay? So I'm going to put it test 4, okay? Different folder. Right? Then you choose the MDK ARM version 5. Make sure that you use this. Okay? Don't forget about that. Then go to code generator tab. You select the second one for the library package. Okay, copy only the necessary files. You can optionally, up to you, you can click on the backup previously generated files as well. Then here, you set all 3 pins as analog. Okay? Click OK. Right? So now you have a project. You can save, because I don't know what games you install on your PC, and you may interfere with the CubeMX. So save the project so that the data will not be lost. And here, you can go back to the description and see what are the things that you need to enable. So here, it says you need to configure GPIO pin 5, okay, PA5 as output, and PC13 as an external interrupt. But as you can see, it's already assigned because we choose the NuCleo. Okay? So here, PC13 or PA5 is an output mode. Okay? So it's already configured as an output. Then PC13 is external interrupt. Okay? So just double confirm that. Then the rest, you don't actually need for this particular exercise. So you can just put it to reset, or you can leave it as it is, or you can just put it into reset state. Okay? So that you'll have a clean project. And here, this one here is for your SWT. Okay? Alright, simple as that. Once you're done, go to the clock configuration. And what is the configuration that we're asking here, or that we're being asked? To configure the system clock in 16 megahertz. Or you can choose whatever megahertz that you want. Up to you. Okay? So 16 megahertz, I can put 16 here immediately. So this is another demonstration. If you put 16 and press enter, it will complain. Okay? No solution because you are using currently MSI as the clock source. And the MSI is only up to 4 megahertz. If you drop down here, see the drop down, it's only 4 megahertz. So it will complain. But it will ask you, do you want to use other sources? So you click OK if you want. Okay? So in this case, it will automatically select the next available one, which is HSI 16, which is getting the frequency directly from the internal RC. Okay? Or you can use the PLL if you want, but doesn't make sense. Okay? To lower down the power consumption, it's better that way. Because at least you don't need to turn on the PLL block. And therefore you optimize your power consumption. So 16 megahertz, check the rest of the profile, 16 megahertz. This is what I want, fine. So let's proceed. Go to the configuration, go to the GPIO, and have a look at each of the GPIO pins that you configured. So PA5, which is driving the LED. So no pull-up, maximum output speed, you can set it to fast, okay, or high or whatever, or just low because it's just toggling of the LED. Okay, so let's say let's put fast here. You can change the label if you want. Then you can go on the PC13, which is the push button, and configure it as external interrupt mode with what? Falling edge. Very good. Alright? Pull up, pull down, you need? No need. Okay, why? because, okay? So this one here, we don't need it, okay? So external interrupt mode with falling edge trigger detection, okay? So once you're done, click OK. Then, that is the peripheral configuration, meaning you are, what? Enabling the EXTI to generate the interrupt request when there is a falling edge. So, the next thing that you need to configure is the NBIG sign, okay? NBIG. Look for EXTI. So, this one here, line 4 to 5 interrupts. So, you configure it like that. You can set it to a lower priority than the system timer. Usually it's like that. We recommend it to be like that. So set it to 1. Okay? And make sure that it's checked. Then click OK. Alright? You can also go to the RCC if you want. You can enable the pre-fetch if you want. Okay? Up to you. Alright? Anything that we missed? Okay? We are on the same page? Yes? Good. Save the project. Generate the report if you want, or just generate the code. Okay? So click generate code. It will generate this code here. Then we open up the project. Okay, so just click open project. So now we have a file project with the necessary files and the initialization code that we have for the peripherals that we have enabled. So double check if the configuration is exactly the one that you have set in the CubeMX. So here is the clock security, the system clock to generate the 16 megahertz. So you have HSI and you're enabling it. There's no PLL, and here you select the clock sources for the system clock, which is now HSI, and there's no prescaler for the peripheral buses and the high-speed bus. So that's why you have divided by 1 here, which means you want the peripheral bus and the system bus to be 16 megahertz as well. Okay? GPIO initialization. So you might wonder, I have only enabled 2 pins, 1 output, 1 external interrupt, and another 2 pins for the debug. But why do I have so many initializations here for these IOs that I did not even enable? Why do I have this? Raise hands. Yes, why? Very good. Because in the CubeMX, we set it to analog. So any pin that is not configured is automatically configured as analog. So that's why you will find here, you see, you will find all these pins that are not enabled, you will see it analog mode. Okay? This is to what? To disable the what? The switch hat, sorry? Yes, reduce the power consumption because it will turn off the switch trigger. Okay, inside. Very good. So you have other initializations there. That's why when you configure your pins, make sure to reserve the SWT pins. Okay? Make sure you reserve the the debug pins, because if you set the CubeMX to convert to analog mode, the unused pins, and you did not configure the SWT pins in your pin assignment, then it will also reconfigure that particular pin. So you may be able to download and debug, download and program the flash at the very beginning, but when you start the code, you will lose the debug. Why? Because it will reconfigure the pin as GPIO pin or as analog mode. Therefore, you lose the SWD pins. So that's why, first thing you need to remember is to set and assign the SWD pin in the CubeMX. Okay. Alright, so we're done with the configuration. I'm going to save. I will help you in the next step instead. Okay. So, where are we now? We have the code, and now we are what? Ready to write some codes. In this case, you don't need to write. In fact, you copy and paste on it. Okay? This is the first thing that you learn in this session. You copy and paste. Okay? Learn how to copy and paste. So, what you need to do is just copy these sections here. So, I will copy it. Copy, and you put it at the beginning, the sections at the beginning. Okay? So maybe you put it under this one here, variables. Paste. So that's one. Next, you copy this section for the begin user begin tree. Copy this. Okay. So this is assuming that you're writing your own code. So look for begin tree. So here, begin tree. Put it there. Paste. Then some more code. Next slide, which is this one. Copy. Put here. Copy. And paste. So this will complete your main loop. Okay? And take note of the question marks. You need to replace it. There's one more thing that you need to copy. Scroll down. And you need to copy this section for the code begin for. Okay? So this section. Okay? And you look for code begin for. Scroll down. This part of the code is actually the callback when you trigger an interrupt. Okay? I will explain this later on. Okay. So, for sure, when you try to compile, okay, when you try to build, it will create some errors. Why? Because there are question marks here. There are missing parameters here. You need to replace this with the correct one. Okay? Okay, so there are a couple of errors. So I will help you with this exercise. So here, the code is actually the the behavior of the code is like this. I will explain the behavior of the code now so that you'll understand. Okay, it's like this. When you run the code, it will blink the LED. You will see a blinking LED at the first execution of the code. When you press the button, it will trigger an interrupt and it will change the mode selection variable, such that when you press the button, the LED will turn off. Okay? When you press the button again, the LED will turn on. When you press the button again, it will go back to the beginning, the default setting, and the LED will toggle. That's the expectation. That's the expected output. So here you are able to trace it. Okay? This one here is toggling LED. This is the default one. The next one is it is turned off. The next one is it is turned off on, and then once you press again, it will go back to the default or the toggling LED. Okay? But before this is you are able to do it, you'll have to complete the code first. Okay? So I will help you. So here, from toggle pin, so this is one of the API to toggle the GPIO. So what are the parameters that you need to set here? You know that the pins that you're using, the pin that you're using to toggle the LED is called PA5. So port A or GPIO A, pin 5. So which means the parameters that you need to pass here should be GPIO A, and this should be GPIO pin 5. So how will I know that I'm using the correct pin? So you can actually go to the definition from here, and you'll see a description of the pin. Okay, description of the parameters. And here you can also see, you can have a look at the what? You can have a look at the header file of the GPIO. Okay, what you can do is you can click on GPIO, and I think you can. Okay, from here, should be able to find. Okay, or you can launch it by clicking just the GPIO pin 5, and it will go to GPIO, the header file for the GPIO. Either here, you can also see from here, you can actually open up GPIO header file for the GPIO. Just click on GPIO C, and you look for GPIO H, okay, the header file for the GPIO, which is this one. So double click, and it will open up this one here. And you should see all the parameters. And you will find a definition for each of the pin. So here, you will need what? GPIO A, and then here, GPIO pin, what? Pin 5. Okay? So look for pin 5, which is this one. Highlight and you copy. Okay? And replace it. Paste. Okay? So that is for question mark number 1. Question mark number 2. Here we are trying to turn off the GPIO. So what will you put here? What parameter will you put here? You need to put what? You need to go to definition. So double click on the function, right click, go to definition, and you'll see a description here of the different parameters. Again, which one? Pin reset or pin set? You need to use pin reset in order to turn on. Copy, go back, replace. Okay. So that is to turn off. The next section or the next selection is what? To turn on. So what will you put here? You put what? To turn on the LED, you need to say, you need to put what? Pin set. Okay. You need to put inside. The opposite of reset. Okay? So this will toggle, because it's using toggle GPIO or toggle pin. This will be turned off because you're saying write to the pin a pin reset, meaning you're writing a 0. Okay? And here you're writing a 1 to the pin to turn on. Okay? So this is for your main loop. And then the other one that you need to change is the last one, which is the callback for the external interrupt. And here, what do you need to do here? This is just debounce, a very simple one, by the way. Okay? So here you need to set, you need to read which pin. You need to read GPIO EC13. Okay? So you need to put pin 13 there. So I go to GPIO H, I look for pin 13. Okay? A pin. So here you are reading the pin. What is the state of the pin? Am I still pressing the pin or not? If I'm still pressing, I will loop inside the while loop. When I release the pin, then I will continue. Okay? Very simple debounce. Okay? Sometimes it works, sometimes it doesn't. Basic. Okay? Alright? Questions? None? So you compile the code. So go ahead and rebuild. So you try rebuild all or just build. It will try to build the GPIO C. Yeah, so I mean that C and the other files that you have, what you call this, that you have changed. Okay? Questions? None? Then you're ready to what? Ready to go into debug mode. So how do you do that? You have done you have built your project. There are no errors. There are no warnings. Then you go into debug mode. So you click this button here, or you go to debug menu. Then you click start debug. Okay, or just press the icon there on the toolbar. So you should see this something like this here. And then, which is programming the flash of the STM32, and you will know that you are in debug mode once you see this toolbar. When you see this toolbar, it means that the Kyle IDE is in debug mode. Okay, so you can close some of the windows. I usually close this. I usually close the disassembly unless if I want to see the assembly code. Okay, and from here. You have several buttons that you can use, run, or you can just single step. Okay? So if I press run, the code, the first thing I will see is just below the, just over here, okay? Just over here you see blinking green LED, not this one. This one is for debugging. You know that the debugger is working or is doing a debug session when this LED is blinking, so it's doing some communication. You should see this LED blinking. Okay? This one just near the push button. Okay? Alright? And try to press the button. Okay? Try to press the button. So the first behavior is what? When you run, it is blinking. When you first press, it will turn off. Okay? The second press, it will turn on. Okay? The third press, it will go back to blinking LED. Okay? Okay? Are you getting the same behavior? If it is not working, it means that you did something wrong. There's a question. He wants to go to definition by right-clicking on the function and then go to definition, and there's a pop-up that says you need to do something. What you need to do is just build the project. Because in Kyle, it needs you to build the project so that it will do the linking, okay, to the different function. Then you can use the go to definition feature. Okay? Are you seeing the blinking LED? If you're not seeing a blinking LED, you blink yourself. Okay? Okay? Questions? No questions? If there's none, I will proceed. Okay? Yes. You have error. What kind of error? Here I think you're missing something. You're missing some files. Okay, if you have problems, we will solve that later on. And just raise your hands, and our FAE there, which are busy, I don't know what they're doing. Is the FAEs? Is the FAEs? Only okay, so if there are questions, could you accommodate? Okay. So if you have questions on exercise number 1, could you raise your hands? Then they will assist. Okay, I will proceed. All right. So just to recap, what is happening when you are trying to push the button? Okay, this is what's happening. Okay, just for your understanding. When we push the button, it triggers an interrupt. It will trigger an interrupt request. So normally, when you are running your code, it will run the code inside the main while loop, right? So it's toggling the LED at the first instance. Okay, so it will toggle the LED. As soon as you press the button, it will trigger an interrupt request. Then the NVIC will jump to the system will jump into the IRQ handler, which is going to the IP.C. Then it will eventually execute what we call the IRQ handler. And inside the IRQ handler are some flags checking and clearing. Okay? And eventually it will call the EXTI callback, which is actually a user function that you need to add and put in your own code. So here it will call the callback, which is what? Inside the main.c. So remember, we copied something into the user begin for, which is the callback. It will jump to that callback, and here, this is where we change the mode setting, right? So it will finish the callback, it will return here, and then eventually it will exit from the interrupt handler and go back to your main. So that's why when it goes back to your main, it will turn off the LED. You press again, does the same thing, change the mode selection variable, then it will turn on. Then if you press again, it will go back to blinking LED. So this is the same scenario when you are enabling the interrupt for the other peripherals. It will have something like this, and it will do some checking of the of some flags internally to clear the flags, and eventually you'll have to choose which callback to use. Okay? Alright? So if you need more detail on this, you go ahead and download the user manual, the HAL driver user manual, to see how the callback works, or to see which callbacks are being is available for you. Okay? Alright? So that is for interrupts. Similar scenario for the other peripherals. Let's say you enable the receive interrupt for your serial port. So when a byte is being received, it triggers an interrupt. So the same flow will happen. Okay? Alright. Let's go to interfacing with motion sensors. Okay? Now, what you call this? The shield that we are going to use to interface with the sensor is the MEMS shield. Okay. Now this is not only MEMS. It also includes some environmental sensors such as pressure sensor and the humidity and temperature sensor. So these are the part numbers that is used in this shield. So you have LSM 6DS0 for the accelerometer, and you have accelerometer and gyro, so two sensors inside. Then you have the magnetometer, you have the pressure sensor, and then you have the humidity and temperature sensor. Okay, so these four devices are in this particular shield, and we are trying to interface with that, or with those. Okay, so let me introduce the different parts. So this device is one package with two MEMS, motion MEMS inside. One is accelerometer, and the other one is the gyroscope. What's the difference between the two, by the way? When you say accelerometer, it's trying to measure what? Linear acceleration, up and forth, sideways, up and down. Okay? That's what it is trying to measure. Gyroscope is what? It's trying to what? Angular rate. Sure, but what is angular rate? It's trying to measure change of angle. Like this angle? Yes. It's actually this. You have like this, and you have like this. Okay? So you have pitch, you have yaw, and you have roll. Okay? So it's trying to measure the angular rate, the rate of change, the rate of turning into this particular axis. It's trying to measure that. Okay? So for these devices, it's usually I2C interface. And these devices will have a couple of interrupt lines. Okay? Usually used to indicate that the data is ready, meaning the CPU or the MCU is now able to should access the data register to read the raw data. Okay? Or these interrupt pins can also be used to wake up the MCU. Okay? So let's say your device is like this. If you are not operating it for a few minutes, then it will go into shutdown mode. But with the accelerometer measuring when you lift the device, it will trigger an interrupt and wake up the MCU. So it can be used like that. Alright? The other one is magnetometer. So it's measuring what? Okay? Measuring Gauss. Okay? So to for all of the axes to measure, north, south, okay, your bearing, let's say. Okay? So that is for your magnetometer. Again, I2C is the main main interfacing, or some of these devices you can also use SPI. Okay? It's either SPI or I2C mode. And again, there are interrupt lines that is coming out of this sensor. Pressure sensor. Okay. So again, I2C for this particular board, and there are interrupts that is coming out also from these boards. So this is the, I will not go deep into the specs of the pressure sensor, but it's trying to, of course, measure pressure in millibar. And two things that you can do, it's either you just measure the pressure or you measure the elevation. You translate, okay? Translate it into elevation. Then you have humidity and temperature sensor. So pretty much know what these sensors is trying to measure. Okay? Again, I2C is being used here. The good thing about I2C is that you can have multiple slaves. Okay? You can have many sensors connected to the same bus. Okay? Now, how do we interface with these sensors? For sure, on the MCU side, you use an I2C. Okay, so in this case, the L0 is a master, because for sure these sensors are slaves, so it will wait until the master wants to read it. Okay. Now you will notice also there are interrupt lines coming from the sensors, because actually the sensors can tell the MCU that, hey, I'm ready now. Please go ahead and read my data. Okay. So depending on your configuration of the sensors, the data rate configuration. Okay? So you can make use of this interrupt so that your MCU could be doing something else while waiting for the data ready from the sensors. Okay? So here, sensors are slaves, and each sensor for sure will have their own addresses. You can configure them through some pins. Okay? And then you can make use of the interrupt and ready signals to use it for wake up event or for triggering for data reading. Okay? Now, the I2C of the L0 is quite simple, like any other I2C, but there is a mode for the L0 I2C which we call fast mode plus, which is up to 1 MHz. Okay, the clock. Okay, so you have the standard mode and you have the fast mode. So fast mode is 4 kHz. Then the fast mode plus is up to 1 MHz. Okay, I don't know if there's a device, I2C device that can go up to here, but it seems that there are a few devices that can go up to this much. Okay? You can configure the I2C as a slave or a master. In this particular exercise, it's a master, trying to communicate with the different slaves. You have 7-bit or 10-bit mode. It supports clock stretching if your device is a bit slow. So it can stretch the clock such that the master will have to wait until it releases the clock. Okay. Then there are some protocols that the I2C is supporting, like the SN bus and PM bus, usually used for power supply. Okay. All right. Questions? Okay. The best way for you to understand how this thing works is to actually look at the code. Okay. So lab 2 is to interface with the sensors. What we have here in lab 2 is that the CubeMX project is already generated. You don't need to do it from scratch, it's already there. The only thing that you need to do with the CubeMX project is to add the I2C interface. Okay? So you open up the CubeMX project, then you add the I2C according to the comments here. Then you regenerate the code. You don't even have to write any codes because, again, it's already a pre-generated project. You are now regenerating the initialization code. Okay? So I will explain. So here, so this is more straightforward. So if you go ahead, if you look at the files, no, the ones that were given to you, you should be able to find, okay, under the workshop folder, you have this, right? You have these files, correct? If you go to NuCleo exercises, okay, double click, then you should see lab 2 sensors. You follow? Yes? Okay. So under the lab 2 sensors folder, you'll see that the project has already been generated. The code is already there, in fact. Okay? Then there's also a CubeMX project that is already there. Go ahead and open it. Okay? Launch the existing CubeMX project. Okay? My tech support people, can we have a look at the other guys? Just check, okay? Randomly check whether they are following or not. So you should have something like this. So it's a pre-configured project. So you will see that the push button is there, and you have LED, which we are not using in this exercise, by the way, except for the LED. Then the SWD is already configured. Okay? The clock configuration is there. Then you have configuration here. Okay? What you need to do is to add the I2C. Okay? Now, I will not do this for you now. I want you to actually do it yourself. Okay? So follow the instruction. Okay? Here in the instruction, this is an overview. What we are trying to do is to set the I2C as master and set it to 400 kilohertz, 7-bit addressing mode. Okay? Then from here, you will find, a step-by-step. So add and enable and configure the peripheral for I2C. You also need to add the USART2 for what? For the virtual COM port. Because what we are trying to do here is that we are outputting the MEMS data through the virtual COM port. Okay? So here, you configure the I2C, you configure the USART accordingly. The system clock is already being configured, so usually you don't need anything here, or just double check if it is properly configured to 32 MHz. Then you set the I2C configuration based on this configuration. Okay? Alright? Now, once you're done with the configuration, generate the code and open up the project. You will notice later on that the project already contains the code that you need to do to interface with the devices. So if you look at the main.c, it's already configured, or it's already written with some codes to what? Okay? Or maybe I'll open up the HAL project. Okay? The project is already pre-created here, except that it doesn't have the I2C and the USART. So as you can see in the main.c, The code is already there. Okay? The code is already there to do interfacing with the sensor. So you see this function, which is a library coming from ESITO, okay? This group from the MEMS people. They have supplied us with some, you see this part here? They have supplied us with some drivers to interface with their sensors. Okay? So what I did for this exercise is just I import the files manually myself. So I used the CubeMX to generate the initialization code, and then I added the MEMS drivers later on. Okay? And then I wrote my user code to initialize the MEMS sensor and then to read the MEMS sensor. Okay? So what is missing in this code is the I2C. There's no I2C here, and there is no USART as well. Because here, if you look at the MEMS handling of the data, there are some missing question marks here, so you need to replace it. It's actually reading the MEMS data and it's sending the raw data through what? It's sending the raw data to the USART2 or through the virtual COM port to your PC. Okay? So there are two peripherals that you need to add using the CubeMX. One is the I2C, the other one is USART. Okay? So that is what you need to do. So I will show this so that you know, so that you have a reference on what configuration that needs to be done. Okay? You have 5 minutes. Okay, so I'll give you about 10 minutes. 10 minutes to do it, so at least it's already configured. So just open up the CubeMX and add the I2C and USART, then follow this configuration. Okay? If you have a question, raise your hand. Don't be shy. I'm not going to bite. This is not an exam, by the way. You can ask your neighbor, you can copy of your neighbor if you want. If you want, don't worry, you have the whole level to drop. Okay, so it's 3:30 and it's time for a break. If you want, you can go ahead and have some coffee, refresh your mind, okay, then come back and do the coding again, right? So if you want, go ahead and have your coffee, some snack, and then you can quickly come back here and then you have your coffee on the table. Okay? So coffee break. Anyone? You don't like coffee? For some reason, the coffee in Vietnam is quite good. I tried to buy coffee beans here, and I tried to buy also the. I bought the dripper, coffee dripper. Go back to Singapore, try to make the same thing, and it doesn't taste the same. My goodness, I cannot recreate the coffee here for some reason. So you're very lucky. So go ahead, have your coffee, and then come back, and then about 3.
chỉ các hiệu luôn. Còn cái hình hiệu nó theo xếp hạng. Lấy cái hình kia về đó, con rồi chưa? Đó, con đi sang kia rồi. từ thì con cảm nhận khi con cảm nhận cái đâu của con mới bài ngày nào cũng sẽ không bắt mời con từ cái đặt vào tàu cái đặt vào qua cầu thôi không được đâu lâu thì có sao đi để như vậy không biết cái kinh tế cả châu biết giờ là mình có đợi đây thì cần kẹo Thì lấy cái một giờ thôi, 3:15 mình mới
Okay. You can bring your copy over if you want. If you want, you can take away some of the food there if you want. So I'm gonna resume now. Okay. Okay, at least some of you managed to show something on the telephone. Okay, good. So if you don't mind, I'm going to proceed with this by explaining. You can still do some catching up if you want while I'm discussing the thing. All right. So this requirement here is based on how we interface with the device. Okay, so it's not really selected by yourself, but you have to understand how the slave works. So these are the specs that is provided by our MEMS team that you need to set the I2C master in this manner. Okay, then the USART part. Okay, you can even show lower baud rate or higher baud rate if you want. Okay, up to you if you want to do that. Now, the final output is actually this, where you have a tumbling LED when it's properly working, and you have to use a terminal software in order to view the messages that is being sent out to the virtual component. Okay, so here we're using a free tool called Terraform. This is quite common. So under the utilities, okay, so inside the workshop NuCleo exercises, there's a utility folder there. You need to unzip the package and execute or run the TTEM code. Okay. Then you have to go for a bit of configuration of the Terraform. So here is the basic configuration that you can try to do so that you can have a readable message, you know, on the window. Okay. So these are some of the tips that you can use if to search for the functions that you need to use to initialize and to read the raw data from the MEMS sensors. Okay, so make sure that the function window is enabled, and you should find something at the bottom like this one here. And again, click on that one and go into the different C files or the library for the sensors and look for the correct functions to use. Okay. So if you read into the comments, you should find the files that you need to open and to search for the correct functions. Okay. Okay. So I'm going to show you what I got. So this one here is the configuration for the I2C. So somebody was asking me, I cannot find when I enable the I2C, it's configured on the I think it was PV6. Yes, okay, PV6. How can I put it to PV9? So again, you need to remap it manually. You need to map it by clicking on PV9. Okay, and then you assign it there. Okay. So although you can do a configuration using the left-hand side, but it will make use of the default assignment. So since your hardware is using PV9 and PV8 to connect to the sensors, then you have to remap the I2C peripheral on this thing. So you have to do it manually. So this is one criteria. Then the USART2 by default is always this one. Okay? So just make sure that the mode of the USART2 is what? In asynchronous mode. So you have to select asynchronous mode for USART2 and it will turn into green, which means it's properly configured. The clock configuration is 32 megahertz, so I don't think that you need to do anything here because it's pre-configured. You can try to lower down the frequencies if you want and try to play around with it. Then you start configuring the I2C. So I2C configuration would look like this. So you have fast mode so that you can reach the 400 kilohertz. If you use the standard mode, then it's only up to 100. Okay, so fast mode is up to 400 kilohertz. The rise and fall time, you set it to 250 and 100 nanosecond. Then you leave the rest by default. You can disable the analog filter. So it's better to enable the analog filter. This is a what you call this? This is an additional feature on the I2C pins to make sure that the even though there's some glitches or some glitches on the I2C line, you'll have some sort of filtering on the pins. Okay, so enable the analog filtering. You can enable also clock stretching if you need to support clock stretching on the device. Okay, on the slave. Otherwise, you can leave it as it is. Make sure that it's 7-bit. Okay. Then the USART2. Okay, so very basic configuration. You just need baud rate. The word is 8-bit. You have no parity and you have 1 stop bit. You enable both direction, receive and transmit. Most of it are default settings, so in fact you don't need to do any configuration for the rest. Okay, just make sure that you have the correct baud rate and the length and the stop bits and parity. Okay. Alright, the GPIO is straightforward. We're not even using the push button. It's just the what? Just the driving of the LED, but it's already pre-configured, so you don't have to worry about it. So once you're done with the configuration, just generate the code. Okay, generate the code, and you should see generated code with the I2C. And the next thing that you need to do is to replace the missing parameters or the incomplete file names, like for example this one here. So here, if you look at the code, the first thing that you need to do is to actually, so if you look at the main.c, the first thing that you need to do is to actually initialize the mems. Okay, so there are functions here which I have created to initialize the mems. Okay. Here, in fact, these are coming from, what you call this? These are coming from the library of, from the MEMS library. So as you can see, if you go to the, definition of that function, then you'll see the definition for, or the configuration for the sensors, okay? So you can try and browse through the function to see what are the default configuration and what are the configuration for each of the sensor, okay? So this is the first step to interface with the sensors, to initialize them according to what you want. So again, these are sensors which are configurable. So which means you need to configure the sensors correctly according to your application. So what you're seeing here is just some of the settings that you can set. Of course, there are more registers that you can actually play around with. Okay? So this is the first step. So once you're done with the initialization and there's no error when you're trying to initialize, meaning the I2C is working properly and the device is is responding properly, then you should be able to proceed to the main loop. Okay? So in the main loop, this is again up to your ability. This is a very simple implementation. Okay? We're not even doing any interrupts in this case. We're just doing a polling mode. So if you look at each of the handler for the sensor, so let's say for the 6-axis, you go to here, and you will find that there are functions that you need to use to access the register of each of the sensor and read the raw data. So this is one of them. This is to read the accelerometer, and this is to read the gyroscope. So you'll have to use the correct functions. I'm not creating this function myself. It is being provided by the MEMS division, by the guys who are doing the MEMS. They provided the library for us to use. Okay? So what you need to do is just open up the 6-axis C file, which is this one. Okay? Using the functions, okay, here, tab, you go to the 6-axis file and look for the function that reads the raw data, okay, or reads the data here. Okay? So you can make use of the get access if you want. You can also make use of the, there are two things that you can use. The one for the gyroscope and one for the accelerometer. Okay, so this one is for the gyroscope, and this one here is for the accelerometer. Okay, so use the G underscore get access and X underscore get access. Okay, for these two ones. Okay, all right. Then for the other sensors, you do the same thing. You look for the missing, you complete the function, and to make the story short, I just show you the complete one. Okay, so get access for the X and G. Then for the magnetometer, it has a similar naming, so you can immediately identify it. Then for the pressure, you have get pressure, and you also have a get pressure, and then you have a temperature, humidity, and temperature. Okay. Now, if you look at each of these functions, you will find one at the last. Okay, at the end of the function, you will see UART transmit. So what you're going, what is being done here is that you're sending the data to the virtual component. Okay, so this is the part here that actually sends the data to the virtual component. Okay. Okay, so this is very basic one. I mean, this is not always the one that you need, but at least you have some sort of an example on how to read the data and how to send the data or where you send the data. Okay. So this is again up to you. There is no processing here. What we are trying to do here is just to read the raw data. That's it. You're just reading the data from the MEMS and you're sending it to somewhere. It's up to you whether you want to send it to somewhere or you process the data. Then you do whatever you want to do with this processed data. Okay. Whether you want to count the steps, whether you want to do navigation based on this raw data, and so on and so forth. Measure the elevation, for example. Okay. Detect a free fall, for example. Right? So it's up to you. So it means raw data needs to be further, needs to be processed further. Okay. So once you are done with the configuration, try to compile and make sure that there's no error, and you download the firmware, the code to the L0. You can go into debug mode, or you can just click load, without going to debug mode. So I'm going to click run. So it's doing it's executing the code now. And you will know that the code is, or the devices or the sensors are initialized and the device, the MCU is communicating well, is that when you are seeing some the LED blinking, okay, in this case every second. Okay, so what you need to do is open up the TerraTurn. So I'm going to open up, and you should be able to see some messages that are being sent out. Okay, serial. You look for the COM port for the ST-Link, which is this one for me. Then you configure, you set up your serial port. Okay, and it's using 1152. Okay. Not quite sure why my telephone is not working for the Give a minute here now. So, any questions with this exercise? Okay, there's something wrong with my character, it's not showing anything. But were you able to make it work? Okay, this one is okay. So what you can do to double check is try to move around the board. Okay, tilt it, rotate it, and you should see the accelerometer and gyro changing. Okay. Now for the temperature sensor and the humidity and the pressure sensor, you can touch the sensor and the temperature will change. You can blow also. You can blow to the sensor to change the temperature, or even the sensors. You can also do that. Okay. You can blow into the sensors to let's say simulate the change in temperature, humidity, and the pressure. Okay. Okay, I'm not quite sure why my character is not showing anything. Okay, so question? I'll try to fix this. Yes?
Đó. Từ thứ 6 gì không á? Thứ 6 gì nằm ở thứ 1 trễ này. Sau giữ anh về thứ 2. Anh ơi số anh.
There are some examples that you can now so there is a partnership and What you can do is so I will proceed if everything is working. If this is clear, then I will proceed. Take note that, again, there's no data processing here. We're just reading the data and sending out. Now, I was talking earlier, there is actually a fusion engine, okay? Asito can explain more on this, but you can download a freeware. We have partnered with a, I don't remember what you call this? I don't remember the exact partner, but you can actually download a freeware from a library from ST. I think if you go to the Shields, I'm not quite sure if I put it in here. Under the Shields folder, you should go to the MEMS. And if you look at the package, you should find this one. Okay? This zip package. This one is a fusion engine. Okay? You install this, then it will install, unpack the library for that includes the fusion engine, and there are some sample codes that you can try out. So more details, you can actually go into the what do you call this? You can go xNuCleo, okay, st.com xNuCleo, and then it will enumerate all the NuCleo boards, all the shield boards, which can be used for the NuCleo board. Okay, so just okay. So these are all NuCleo board expansions. So you'll see different NuCleo boards, and if you go to Motion MEMS, okay, you click on this guy. I think it should be this one. Okay, let's start with this. And it will show you a couple of libraries that you can use. The library that we are using today in this session is just a simple library which basically talks to the MEMS, but it does not do any processing of the data. Okay? It's just a simple driver to interface with the MEMS, to configure the register and to read and to write. Okay? So here, from this web page, if you scroll further down, you should find this part here. The library that we are using for today's session is this library, the MEMS library. Okay? So together with the STM32 Cube library, I have added the library from the MEMS, which is this one, this package. Okay, so you'll find it. These are this one. Okay. These files. Okay. This is what is included in the in that particular package. Now, for the Fusion, you have this real-time activity recognition software expansion, and you have also real-time motion data fusion software. Okay, so if you click on that, the OSX Motion FX, it will give you. You can download the library, and here you have some sample codes to actually implement some of these features where you can find on your for what you call this, for data processing of your MEMS data. So just load it. So here, so it's a data fusion that basically will fuse the data for the gyroscope and the accelerometer, including the magneto as well. Okay. So here you can implement some sort of a an application, and here instead of writing your own algorithm to fuse the different sensors, you have a ready-made one, okay, that you can use. So the other library, okay, the other library is actually is much simpler, which is this one here, activity recognition. This is to measure the number of steps and so on and so forth. So if you open up the package and it's coming from the same third-party partner that we have engaged with, okay? So it is providing you with a set of APIs that you can use. So the data fusion, it's actually doing quaternion and all this, what you call this, transforms basically. So this one here is for the activity recognition, and the API that you will find here in this particular package is for what you call this, is to implement. It should show up here. Is to implement this walking, fast walking, jogging, biking, driving. Okay? So there are sets of APIs that will detect this activity, and all you need to do is execute the API, and it will return you with the status. So this one here is a little bit of fusion. So it's processing the raw data. So if you want to know more, just download this, and you should be able to run some sample codes. Okay? Alright, so that is for the MEMS. Now, the next part here is actually sending the data through Bluetooth. So, in the, okay, before I move to the Bluetooth part, there is an optional demo here that you can try later on. Okay? So, you can try the optional demo, which is actually to use some of the utilities from the MEMS drivers, okay, the one that we are using now. Okay, so what it is doing is that there are some. If you unzip the Xcube MEMS1 library, you should be able to find some utilities folder where you will find some PC GUI. Okay, and here, if you install it and run the corresponding projects, you can actually use the GUI, let me see, like this, okay? A GUI that is included in the library, and to show you, instead of numbers, like the one that we see on the virtual comfort, you are using now the GUI to translate it into graphical representation like graphs, okay? Okay? So it's the same thing, it's using the virtual comfort to read the data, and the GUI is fetching those messages, and it's showing it as a graphic graphical representation of the data. So you have graphs here, and you will see also some activities here, some the numbers that you are actually seeing on the virtual component, and this would be the graph. So at least when you try to move around the cube, the board, you will see the graphical representation. Okay, so that is an optional demo that you can try out. So you can do it later on. I will proceed to the interfacing with BLE. So this time around, instead of sending the data to the virtual component, we are now also sending the data through the Bluetooth. Okay? So we are going to use BLE Shield for this. And we're using, in the BLE Shield, we're using the Bluenergy chip coming from the Bluetooth team. So this is the, I think Esito already introduced a little bit of this, Bluenergy. So Bluenergy, with all these features here, so it supports what BLE versions again, Esito? 4.0, 4.x. Okay, so it's, you need to have, the thing is that in order to pair with this chip, your phone should support 4.0 at least. Okay, so if your phone doesn't have this, then you'll not be able to interface or to be able to pair with the Shield in this case. Okay, so we will make use of the Bluenergy chip, and this is just an overview of the device. So I will not go deeper into this. What I would like to show you is this one. Okay, the Bluenergy or the BLE library supports the STM32L0, and here you will find a partitioning, okay, of the software. You'll find that in the Bluenergy chip, inside is actually implementing the some of the stack for the BLE. In fact, most of it is implemented inside the BLE chip. Okay? What you need to add into your MCU is only this part of the stack, which is just to interface with the SPI and just to implement the BLE profiles. That's it. The rest of the layers for BLE, it's done inside the chip. So this will upload your MCU to do further processing or further, let's say, formatting or formatting of the payload to comply with the BLE protocol. It's done inside the BLE itself. What you need to do is just to send the raw data or the payload to the BLE through a set of APIs, which our BLE people have provided. Okay? So this is how it is being partitioned. So they call it Application Controller Interface, or ACI. So there are a couple of APIs that you can use to send the data to the BLE chip. And then the BLE chip will manage the packaging itself. Okay? To package it for BLE protocol and send it out. Okay? So here, in the STM32, so this one here, the definition for the profile, and depending on the profile that you're using, then you will have to use the APIs for that particular profile. So it will make use of some of the dedicated APIs for this type of data exchange. Okay. So, in essence, when you interface with the Bluetooth, in this case Bluenergy, it's using SPI bus. There are some GPIO that you need to configure. It's a mandatory thingy. You have the reset pin, which is basically used to reset the Bluetooth device. It's to reset by hardware. There's also a chip select, okay? And there's also an IRQ on the Bluenergy. IRQ is basically to indicate that there's a data that the MCU needs to read. Okay? So especially when it's receiving some packets from the host, the other BLE device. So when it's ready to be fetched, then there's an IRQ that you will see. Okay? So this here in the implementation for the interfacing, it's IRQ triggered. Okay, it's interrupt triggered by the BLE. Okay, so we are going to use one GPIO configured as an external interrupt, and then in the external interrupt callback, there are some functions there that actually will access the BlueNerd library, okay, to fetch the data coming from the Bluetooth chip. Okay, so on the L0 SPI peripheral, these are the different features. Can go up to 16 megahertz of bit rate. You have 8-bit or 16-bit data size. You have for sure the slave select, and you have two configuration. One is a hardware slave select or software slave select. Okay, so these are different formatting. Most significant bit for this significant bit first, 8-bit or 16-bit long. Okay. Then different SPI interfacing. This one is a common interfacing. Okay, so where you have a master, you have the clock of the SPI, and you have master in, and then you have also a master out, and you have a slave. And the slave select, it's connected permanently. Okay. Sorry. Now you have the possibility to actually free up the slave select pin by using the software management for the slave select. So in this case, you only have 3 pins connected between the slave and the master, and you can free up the pin and use it for something else. Okay. So this is what we call slave the software management for the slave select. Okay. All right, so for the BLE exercise, the same thing as what you've done earlier on the sensors. There's a project that is already created. You just now need to enable and add the SPI. That's it. The I2C and the USART is already pre-configured, which means you don't need to touch this. And the codes to read the MEMS, the sensors, is already added in the project. Okay? So here, this is the interfacing now, where you are reading the raw data from the MEMS shield to the I2C, similar as what we have done in Lab 2. And instead of just sending it to the virtual COM port, you're also sending the same data to the SPI going to the energy chip. Okay? Right? So now the BLE here is now sending data out. But of course, you need to pair the BLE to to another controller, to another BLE device. And in this case, you'll have to use the smartphone. Okay? So make sure you have a smartphone that supports version 4.0. Hopefully, most of you have having these smartphones. Okay? If not, then it's a bit of what do you call this? It's a shame, you'll not be able to see something. The output here, what you will see, okay, later on is on your smartphone. You need to download. This is an example from Google, from Google Play. You download from Google Play or from if you're using Apple, okay, then you can download the app called BlueNerd app. You download and install, and once you enable the Bluetooth on the shield, you should be able to find the BlueNerd here, and you pair with the BlueNerd through the GUI of the app here. And what you will see once it is successfully paired, you'll see a cube, which represents the rotation of your board. So if you try to rotate it like that, then you will see the you will see the cube turning. The device, this one up for the boards. I don't know. Alright, so you have this app that actually shows you a representation of the board being rotated. You have also an app, you have also a representation of the temperature and the pressure sensor and the humidity. Okay? So instead of just seeing numbers, you're actually seeing some graphical representation of those numbers. Okay? Through an app on your phone. But again, you need to have the correct version of the Bluetooth on your phone to be able to do this. Okay? Alright? So I will give you around 15 minutes to follow the instruction as indicated here on the Bluetooth. So you open up so I will show you. So you go to the exercises, and you should find lab 3, Blu-ray plus sensor, okay? So here, you also have the project, the CubeMX project. Right? So it's a pre-configured one, so the interfacing for the MEMS is already there, so you don't need to touch the I2C and the USAR. What is missing is the SPI. Okay? So you need to add the SPI and configure the SPI according to the configuration here, which is explained here. Okay, this one, right? So once you're done with the SPI, go ahead and compile. Okay. When you compile, when you generate the code, then you should be able to launch the project. And here, the same as in Lab 2, all the library files for the MEMS, and now the library files for the Bluetooth is already there. You don't need to add them manually. Okay? Then the only thing that you need to change here is the Bluetooth address. Okay? A Bluetooth address. Okay? Because imagine you are, imagine you are turning on all of your Bluetooth together. When I look at the phone, I have a list of all Bluetooth there. And it will look like this. It will have the same thing as this. This one here. You will have a list like 1, 2, 3, 4, 5, many. Okay? So, in order for you to identify the board that you're using, you need to take note of the address of your Bluetooth. And this address is user configurable. Okay? So here, you can, part of the code is to actually change and make sure that you have your own unique, address. Okay? So there's a slide for that. Okay, this one. Okay. So it will show up here. So it's just follow the direction. You're reading this way, it will show up this way on your GUI. So in order to get the right, unique address for you, let's assign something. There are 3 zeros here, right? 0, 0, and question mark. You can change these two. Okay? Change these last 2 zeros, last 2, according to your seat number. Okay? So I will assign. So listen up. This one is row 1. This one is column 1 and column 2. We'll make use of 3, by the way. Sorry. 1, 2, 3. You'll have to change this. This one is for column. This one is for row. Okay? And this one is seat number. At least you will have a unique one, right? So this one is column 1, and you guys are column 1. So which means this one is 1. You guys, this will be 2, meaning 0, 2. The row number is, this is row 1, row 2, 3, 4, 5, 6. Okay? So you put the row number here. Then this one here is the seat number. So we start with this one. 1, 2, 3, 4, whatever. 1, 2, 3, 4, whatever. Okay? So at least you have your own number. Take note of your number, and then when you turn on your Bluetooth and open up the app, make sure that you select the correct Bluetooth. Don't connect with the other one. The guy will say, hey, why is it not turning as I want? I'm trying to change the temperature, but it's changing the humidity. Or it's changing the pressure. Why is it? I'm not turning the cube, but the cube is turning now. Actually, the other guy is okay, messing up with you. So, make sure, take note of the number and pair with the correct one. Did you get this? Did you get it? Alright. So you have about 15 minutes. Okay? 15 minutes to do this. Alright? And if you don't have a Bluetooth 4.0, just let us know and we'll try to use our phone to connect to your device. Okay?
Tích sửa nữa người dân mới phải chụp hình không sáng sáng nhà đi sẽ thành cái quen đấy bắt đầu sao thế
Right? Okay? All right. So what do we have here on the configuration for the SPI and the what do you call this? SPI for interface with the lunar gene. This one is an example. Okay. So the SPI would be this one. Oh, sorry, the SPI would be. I should use So the SPI is this one, this tube here. Okay. And you also have the clock is over here. Okay. We need to do a little bit of remapping in order to assign it to the correct pins. Okay. Then you have the IRQ pins and the chip select pins and the reset pins. So these are essential to interface with the Bluetooth. The configuration is a bit straightforward for the SPI. It's only a couple of settings. So you have frame formatting, you have Motorola. There's only two versions, TI or Motorola. Then you have 8 bits, most significant bit first. Then you set to 8 megahertz. Okay, so you need to set the correct rescaler in order to generate the correct megahertz, let's say megabits per second, your bit rate, your baud rate. Okay? The rest are basically for the polarity, which I think is the default setting low, and then the phase, the first edge. Okay? The rest, you can leave it as it is. Okay? So once you have generated the project, you should then try to change the address according to the row seat number, okay, that I have assigned for you, and try to compile. So again, when you do this, it's the same. You will still see the character messages, but at the same time, you should be able to see the Bluetooth, let's say, device on the your smartphone. Okay. So let me just load mine so that I can show you. Okay, so you can go ahead and click load, this one here, right? This icon, so that you don't have to go into debug mode. Okay, so once you're done downloading, try to press the reset button to reset the device. Okay, and it should execute your code in this case. Okay, now I will use who has successfully run it? Who has successfully run the thing? This one? Who? Can you show me? You have a lot, right? So I have, okay. So you can tell me what is your number? Not your phone number, but your Bluetooth number. which is what? 5D. I'm not seeing a 5D here. Too closer. I'm not seeing a 5D now. Who is 01, 04, 05? 01, 04, 05. Okay, let me try to interface with you. Nothing. Okay. Okay, so just check around. So you should find something like, I cannot show anything, it's so small. So but when you try to shake, so you see the cube turning like this. So I'm interfacing with that, right? Okay, with the correct number. And when you try to turn, then you will have something like that. Then if you go to there's a tab here for environment. And you should see temperature. Try to blow something on the, try to blow the sensor. So now it's increasing to 27 degrees. So it means that it's sending the sensor data properly. Okay? You can also lift the thing up, then it should change the pressure. Because as soon as you lift up, then it will decrease something like that. Okay?
So we have questioned whether the source code for this Android and iOS is
that I don't know. That's an Acito question. Acito. There was a question, source code for the app it's released. Okay, so he has to check whether the Android app is you can download it from somewhere. I mean the source code. Okay? Right, so if you're really interested, get in touch with our distributor or with Chao here, and then we'll come back to you on this. Okay? You need to change the p-scaler. Okay, so do you have any questions on this? Don't worry about the answers because the answers are actually, you have copied the answers already. So I'll show you where you can open up find the answers. Okay, so here, from the files that you have copied over to your C drive, the workshop files, right? Okay. If you go to, it should be NuCleo. No, sorry. It should be under, under NuCleo. So this folder here, STM32 L053 NuCleo. And you should see two zip files. The first one, MX answers. Okay. So the answer for lab 2. The answer for lab 3. Okay? So don't worry of not able to finish the exercise today. You have the answers with you. Okay, so I have purposely hidden the answers so that you can actually do the exercise. Okay? But the answers are there. Just refer to the answers. Okay? Any questions? Any questions? The NFC exercise is just a demonstration. So I will just tell you the principle of the exercise. You can follow it later on. It's very simple. The NFC has a what do you call this? They have the organization or the work group has defined a formatting for specifically for tags where you tap on the tag, it will launch the website. Okay, they call it NDEF formatting. Okay, So this type of information you can store in our NFC device, such that when you tap on the tag on the NFC, it will automatically launch the website or whatever information that you put in there. The tricky part is to follow the NDEF format. It's defined by the work group, the NFC work group. You'll just have to follow it. But the exercise for the NFC, the source code is there for you to follow. Okay? So you can use the sample code from the to interface with the NFC shield. And this particular example is actually implementing the NDEF formatting. Okay? So in this particular exercise, it will launch the ST website when you tap. So here, the STM32 will program the NFC chip with the NDEF format of the website. And then when you try to tap, it will launch the it will launch when you tap your, for example, this phone has an NFC reader. So when I tap with the NFC tag, it will automatically launch the ST website on my phone. Okay? And the source code to do that is, you know, the sample code that is provided by the NFC shield package in the library for the NFC shield. Okay? So it's quite straightforward. You just need to refer to the source code. Okay? Any questions? No questions? If you have some other questions later on, get in touch with our distributor or with our HR here, and we will come back to you with the answers. Okay? So if you don't have any questions, then that's it for me. Thank you for listening, and thanks. My name is Jerry, by the way.
Vâng, thì rất là cảm ơn các bạn đã nhiệt tình ngồi lại với chúng tôi đến tận giờ phút này, và một lần nữa rất là cảm ơn các bạn. Hy vọng là cái buổi workshop hôm nay của chúng tôi thì hữu ích cho công việc của các bạn sau này, và rất là mong các bạn sẽ tiếp tục phát triển.